Greetings, everyone. Uh, my name is Stephen Scholka. I'm on the ASQ Board of Directors, but also a member leader in the Statistics Division, which is offering you this presentation today, and then for the next three other sessions on the basics of SPC. So to kick it off, I'm going to read about Jim Bossert, who is your presenter. And Jim is a senior performance excellence consultant with John Peter Smith Hospital in Fort Worth. Prior to that, Jim was the Lean Six Sigma and Change Management Master Black Belt for High Reliability Initiatives at the Joint Commission Center for Transforming Healthcare. In this role, he was responsible for leading and coordinating activities supporting the adoption of high reliability practices with hospitals and state hospital associations. He has been actively involved in quality and process improvement in all levels of management for over 35 years. He has presented at numerous conferences as well as written papers, written books, provided webinars, and shared his learnings. In 2018, he was named Quality Magazine's Quality Professional of the Year. Dr. Bossert has certified green belts, black belts, and master black belts in these industries. And so he is well educated and knowledgeable on the topic of SPC, but we are going to try to make this as user-friendly as we can and give you the basics. So with that, I'm going to turn it over to Jim and let him get started.
Thank you, Stephen. Greatly appreciated. And we're going to spend today talking about variation. The challenge we have is that people hear about variation and they're not quite sure what it is most of the time. So one of the things that I want to do as we go through this is that at the end, you're going to understand basically what it is and why it is important. I'm going to give you more healthcare examples because that's what I've been working in lately, but I'm also going to give you some manufacturing examples as we go through for some of the things here. One of the things that I want to focus on is that a lot of times when we talk about SPC, everybody wants to jump right into control charts, but we have to look at it first and say, why is a trend important? And why is that more important than a single number? Well, if you think about things, how many times when we look, you've been in meetings or you hear people talking about it and they say, oh my gosh, did you hear what that number was? It's 35%. It's supposed to be 50%. And they panic. Well, if you understand variation, that might be well within the confidence interval. It might be within the variation that you're expecting. And so rather than overreact to one number, we want to focus on where is it going, what's happening, because that's going to tell us more what it is. So we're going to talk about some trends, and I'm going to give you a couple demonstrations, and we have a neat case study at the end that I'm sure will be interesting to everybody. And we're going to basically give you how to identify a trend and how to basically get a feel for what to do when they give you data. Okay, so we'll talk about some different tools that are basically ways that we can look at trends and understand what it's doing. So first thing we want to talk about is variation. What is it? Well, the simple one for most of us that are working in quality is basically it's a change in something that's happened, whether it's amount, level, or the quality of a product. And I'm sure we have all bought products and said, well, gee, it seemed to be much better the last time we were there. There's variation all the time. Think about when you're going to and from your favorite place that you like to go. Does it take the same amount of time to get there? Or does it take longer some days than others? For those of us that work, we know what happens when school year starts. School year starts, things take longer to get to work. During the summer, it just flows along. So, we have different variation occurs all the time. We also have to remember variation means a thing differs slightly from another of its type. Okay, if any of you are into things like crocheting or needlecraft, you recognize that fabric will change. And I happen to be lucky enough in one of my past jobs to work in the fabric industry, and it was sometimes amazing the differences from one lot to the next. Um, for those of you that are painters, you may recognize that paint changes from lot to lot in terms of variation of color. It may be very subtle, but when you put one against the other, it may be enough to say, whoa, what's going on here? And you may want to blend them together. So there's things that we see in terms of changes. The other thing is it's a change in the way something works. Okay. We're going to talk a lot about data, and we're going to see data has all kinds of variation associated with it, and that's okay. That's part of the thing that we want to look at, but you also want to recognize that sometimes data can work against you. So you got to think about what it is. In the medical industry, like cardiologists like looking at electrocardiograms because they can tell by looking at the pattern if the patient has had a heart attack, right? Because the pattern is different than if it is a normal situation. It's the same thing with people that have strokes. When they do a CT scan, they can actually tell if a person has had a stroke and where they have actually had it, how serious it was. So variation is around us in everything we do. Now, when we look at variation, here's just a simple example. We look at this variation and you see it and you go, Now, thing is, most of you look at it and say, yeah, okay, but you don't know whether it's good, whether it's bad, whether this is normal, what you tend to see. So, we have to think about, how do we look at it and how should we react to it? So the questions you're going to always ask yourself is, first of all, is this variation good? Ideally, it is, and that's what we're looking for. But sometimes it isn't. So it might be bad, and we need to know when it's bad, and we need to be able to say, how do we know that? So what we're going to spend some time talking about today is how do we know that? One of the things that I've learned in my career as a stat magician as well as master black belt is you got to know how to plot data. I can run all kinds of fancy analysis and do all kinds of nifty things, but 9 times out of 10, people have no clue what you're talking about when you say, "Oh, it's got a significance level of this or a p-value of this." Rather, they look at the picture and the picture tells them something. And that's the kind of thing that we want to focus on. And what we're going to talk about today specifically is different ways to plot some data. And I'm going to start very simple. But as we go through, we have to think about what's the sequence of steps we have to go through to plot data. So you have to, because if you don't know what you're collecting or you're just asking for data, you run the risk of not getting exactly what you need. Okay, so you have to first of all ask, what kind of data do you have? Do you have continuous data or do you have discrete data? We'll talk about what those different things are in a few minutes, but think about continuous data is on a continuum. Okay, so we can do a lot of stuff with it. And for those of you that are getting into mathematics and statistics, you'll recognize, hey, continuous data, that's cool because I can do all kinds of cool stuff with it. Whereas discrete data, I'm a little more limited in what kind of analysis. But the other thing you want to think about is what's the underlying data distribution of the data? Is it bell-shaped or considered a normal distribution? Or is it spread out or skewed to one side or the other? Okay. And then when you collect your data or when you get the data given to you, because a lot of times nowadays we get it from our computer people. Is it in time sequence? So do we have a time order to it? If it is, that tells us that we can do run chart, we can do a time series chart, we can do a control chart. If it isn't, we're kind of limited where you have to do what we call scatter plot or an XY plot, depending on where you're coming from. But those we have to think about what kind of way we want to look at the data. So when I start talking about continuous data, it's on a continuum. And one of the things we have here, for example, is we can look at time. Time is continuous. Those of you that watch the Olympics, you can see how small break time down. The 100-meter dash, they're carrying out it seems like 14 zillion decimal points. Okay. Whereas when they're talking about doing the marathon, it's hours, minutes, and seconds, but it's not carried out as many decimal points because they don't need it. Okay. And then you have weight. What kind of weight do you have? And how are you going to measure the weight? Is it measured in pounds? Is it measured in ounces? Is it measured in grams or kilograms? So we have to think about how we do that and, what kind of measurement are we going to need? And then temperature. Temperature, for the most part, at least for the US, we're kind of got it easy. We talk about Fahrenheit. Okay. But those of you that have the luxury or have an opportunity to travel over to other parts of the world that use Celsius, it may take a little bit of an adjustment for you to get used to saying, okay, what is the temperature today? How do I convert it from Celsius to Fahrenheit so I know what I'm looking at? Okay, so we have continuous data. Now we also can have what we know as discrete data. And discrete data basically allows us to look at things like a binary. That's a good, bad, pass, fail type thing. Fairly easy to do. And, we can do some stuff with it. We can have unordered categories. And, unordered categories, people sometimes get really confused by this, but it really isn't that hard. I mean, unordered categories basically means it's a bunch of stuff that's thrown together. Think of units in an organization. In a hospital, for example, you have an inpatient unit, you have an outpatient unit, you have clinics, you have emergency care, you have x-ray, you have dialysis, you have all these different things. They're all part of an organization, but each one has separate functions and does things differently. Then you can have ordered categories. Ordered categories can be things like percentages or net promoter scores. Net promoter scores is a way that people look at to say, how do they have good customer satisfaction? Another thing of ordered categories that people sometimes don't think about, but it occurs in nature all the time, and that is rainbows. Colors of the rainbows are based on a wavelength, and the wavelength is an ordered category. So you'll see there's certain colors at certain wavelengths. And then finally, another kind of discrete data is count data. How many times do we see things? How many errors do we find? How many errors do you find in a bill? How many mistakes do you find that that a bank has made, or mistakes that are made in typing? Okay. Fortunately, we have spell checkers now, which makes it a lot easier, but still, when you get done typing up in paper, you always tend to find there's some things that need to be addressed, or you have grammar things you got to take care of. Okay, so data types are important. So here's an example of just looking at some distributions. On the left-hand side, you see what we would consider normal distributions in various shapes. Very narrow, some are very wide. On the bottom, you have more of what we call a skewed distribution. Okay, so you have, in this case, we look at the skew and you say, okay, where does it go and how does it work? So skews are very important for us. Then we have scatter plots. And scatter plots talk about, what is going on with discrete data. So is it an XY relationship? And if you see a shotgun pattern, what do you have? You basically have nothing much going on. Okay? So that's one of the things that you're looking for. If you have things going as one increases, the other increases, then you have a linear relationship that's positive. And that's what this one shows over here on the right, as opposed to a negative linear relationship, which means is as y increases, x decreases. So it's going down. And then you can also have nonlinear relationships where you have some curvature going on, and we have to recognize that and work to it. Okay. But scatter plots tell us what the shape is and basically give us an idea of, how well does it match? Because if I have a linear relationship like shown up here, that's a pretty good fit. But if I was trying to define the relationship of the one on the right, which is more of a shotgun pattern, I'm looking at it and going, my gosh, I have no idea where to even begin to quantify that. So you have to start looking at the pictures to get an idea of what to do. So why do we want to plot in sequence? Well, when I look at data over time, it gives me an idea of what is changing. In this case, we can see the graph is heading in a downward direction. I had to draw a single line. I would say that this is a decreasing event, which it might be a good thing. And it might not be. We just, but the point is you need to understand that in terms of what you're looking for and how it works. So somebody gives you some data. What do you do with it? How do you go after it? Well, I want you to think about PGA, okay? And this is not the Professional Golf Association. This is a way to look at data. P stands for practical. Look at the data. Do you see any numbers that are really out of place, or are they missing? Okay, that's the first thing. Then you want to look at it graphically. What kind of data do we have? I want to see where is it centered? What kind of spread do we have? Is the data normal or is it abnormal or skewed? Okay. And then finally, it's analytical. What questions are you trying to answer with this data, and how do you look at it and come up with a conclusion? So by looking at data this way, it gives us some ideas on how to work at things. For example, in this data set, we have mainly missing data here. And, from a practical perspective, missing data gives us headaches. Some software packages will identify missing data and just not use those rows, but some don't. But then you might have some unusual data, like it looks like on the bottom down there, the unusual data you have 459, where nothing else is in the hundreds. So did somebody just kind of hit two keys at the same time? Yeah, somebody just kind of like got distracted and just typed too fast. What happened? So you got to go back and investigate these and make a decision whether or not you include the data or not. And then you look at graphically, what's going on? Okay, what's the shape? And things here are always good to know. This is an example of a Minitab output. Whether you use Minitab or some others, the thing is you can look and say, how many data points do I have? Okay. Is the data normally distributed? Okay. What kind of data do I have with respect to where is it centered? What type of variation am I seeing? So I need to get that and look at it so I understand exactly what's going on and try to figure out, what to do with it. We also look at it from an analytical perspective is the data in time order? Okay. If it is, we can use a run chart or a control chart. Okay. If I think there is a relationship between two variables, then I can use a scatter plot. But if I have more than one group that's being looked at, then, box plots, ANOVAs, some other way, but you want to think about how do you want to analyze it? How do you want to picture it? What do you do with this? Okay. So let's look at variation over time, because that's the whole thing that we're trying to talk about here. how much variation occurs. So I've got something here. We're looking at data over time and kind of made it easy because I put a trend line in there. And so if you look here, you can say, yeah, it's trending up, isn't it? You go, oh, wow, that's cool. Unless you don't want it to trend up, you're supposed to see it flat or go down. But the other thing you're seeing here is you're seeing a thing called cycling. High to low, high to low, high to low, and it keeps going back and forth. So it makes you kind of wonder what's going on. Is this the type of thing where we see somebody making adjustments when it gets too high or gets too low, and so we just see that going back and forth? Or do you have automatic adjustments built in so that it tends the machine or the process automatically adjusts itself, which again can create a sawtooth pattern? Run charts are probably the chart that I like using best to look at data initially if I can, okay, because I want to be able to see what's happening over time, okay. It gives me a chance to basically see what is going on before and what's going on after, which means when I'm collecting data on a project, I'm going to want to collect data from before the project began to see what was that normal variation that I see, so that after we put improvements in place, do we see that time change? Do we see the variation change? Okay, so we want to look at it and think about it. Okay, so run charts are extremely important. The assumptions we make, though, to do it is we have a time-ordered sequence and we know what it is and we can plot it. Okay. Data also has to be collected on a regular basis, whether it's every day, whether it's every week, whether it's every month. We need to have consistent data in there. And we have to have a large enough sample size to detect trends, or cycles. And what's important here is if I go and I say, okay, I need 30 data points, and I collect 30 data points in the next half hour, is that going to tell me if I got a trend? Now, if I take 30 data points over the next 3 days, that's more likely to tell me if I've got a trend. But I might even be able to get more data. So it depends on what you're looking at, but you got to get a big enough sample size. In an ideal world, give me 100 data points. It all depends if you have to collect them yourself, if you have to go back to the computer group, you see it, but figure out what's the best way to get your data. The other thing we're making an assumption at this point is that no changes have been made to the process. I haven't put a new process in place halfway through the data I'm looking at. What I'm looking for is this is a process that is considered stable because we haven't changed anything. Okay, so we want to be able to say that it's working and it's nothing unusual is happening. That is a very important aspect, because if a process is changed, it's going to basically throw off any conclusions we might want to make at this point in time looking at it. So we have to make sure there's no change in the process. The other thing we can say is, there are wide swings over a period of time like this data we showed before. If there are, what's happening? What's going on with this? But I also want to see, and the chart on below is typically what I tend to use, for example, when I have a new process put in place. So I'm running a process, I've got the before data, which is on the left-hand side, and then all of a sudden I go and see basically what happened, and whoa, it shifted down. Now I'd like to be able to say I did something to help that. Okay. So you want to try to identify those where shifts occur and basically use those to show evidence that whatever you did worked. Okay, so this is where pictures can tell you an awful lot, because I could have ran an ANOVA, I could have ran some other type of analysis and said, yeah, this is what it's got, this is what's happening. And people go, uh-huh, uh-huh. But when they see the picture, all of a sudden it's bang, they got it. Okay, so that's something that you want to remember. But, even looking at that, Do I really know? Is it okay? Isn't it okay? Even with the trend chart, I need to understand, do I have to react to it? Is it good or is it bad? So we need to have some type of anchor. And when we put an anchor in place, we want it based on some scientific approach as opposed to guesswork. Okay. Um, One of the things that uh, some of us that have been in the field a while, we hear of targets being made using a technique known as the blue sky method. And the blue sky method is a person's in a room, and kind of their eyes roll up to the top of the ceiling and they look kind of thoughtful and say, yeah, that sounds about right. Okay. That's not scientific. We want to use it based on the variation we see. We want to create targets. We want to create standards. We want to create limits where the data is telling us what's reasonable and what isn't. We also want to react only when it's necessary. I generally don't react every single day on data. I tend to look at more in a week or a month because I want to see what's going on. But if I have a process where I'm making 10,000 things a day, I may have to react every day. I may have to react every hour. So it all depends on what I'm looking at and how I'm doing it. So we have to understand, where is the variation? So, might do a cause and effect diagram to understand what are the process elements. This is where we build in, people and equipment, environment, methods, and materials. And, we also want to understand that we may have some random predictable fluctuations and changes over time just because things happen. And it's just part of the normal process. I don't want to react when there's normal cause variation. I want to act when there is unusual causes. Okay, so common causes, I just let the process go. And that's the hardest thing for people to look at. If they see normal fluctuations, they tend to still want to tweak it a little bit. And we don't want them to do that. This is why control charts, or as I like to call them, process behavior charts, were created. Okay, and the red lines basically are plus or minus 3 standard deviations around the mean. And that says that this is the normal process variation 99.7% of the time. I only want people to react when I'm teaching them about these charts when it goes above or below the line. Okay. Now, you're going to learn how to react when it goes, other patterns show themselves as we go on later on in this series. But right now, you just react if it's over or above. And why do we do that? Well, because people tend to get nervous when they start looking at data. And they want everything to, first of all, they don't understand variation occurs all the time. And so they tend to, every time they see a change, they want to touch something and do something. And I don't want them to. I want them to look at it and think about what it's doing. Because it may self-correct itself. Now, you see one high point here. Okay. And that's basically in January 22. Now, I had a process a number of years ago. I was working for a company that was grinding materials, and the material would go down go into a mesh. And when it was ground fine enough, it would go through the mesh. If it wasn't ground fine enough, they would basically stop the process, put the material back through the grinder and grind it again to make it even finer and finer. But every once in a while, they get a spike above, just like you're seeing here. And they constantly, they were looking at it only within a period of a week. When we expanded it out, we found out every month we saw the same pattern. So by going out every month, we could see the exact same pattern. We knew when we had to shut down for regular maintenance in order to readjust the equipment to get the grinding down to a regular pattern, okay, to a small enough size consistently. So these are things that when you look at it long enough, you can do things. When something's outside of the limits, what do we say? Hey, something happened. And something happened, that's okay. But it is considered a rare event. And it's simply because when it goes outside of the limits, it's happening 0.27% of the time. Really small. Okay. So we need to investigate what happened. What is cool about this is sometimes it happens on the good side. And what we want to do is say, hey, if we did it once, can we continue it? Can we do it again and set a new level of performance? So you really want to build that in and think about how that works. Okay, so we've talked a little about variation. We've talked about some nifty stuff here. I want to spend some time talking about a case study and how it works. Let me give you a little of the background on here. This is a case study that has 46 people. They are all considered they have to have a certain level of proficiency. And so what we're doing is we're measuring this. Now, when we do this, we have to do it on a regular basis. So, if they aren't meeting the standards, then they have to be taken back for more training. And then they have to requalify. Okay. Very typical in most manufacturing operations. Okay. The thing is, the better they are, they could get more pay because what they're doing is we've got a sliding scale. So we want people to perform their best so they can make the most money. And the other thing is this test takes place over 4 days. Okay. They're going to do the same test 4 times, once each day. So they're going to get, breaks and do that. They won't need to basically follow through with it. Here's the data, and I know it's kind of hard to see, but to give you a sense, okay? Some people perform better than others, but which ones? And which ones do you need to basically look at and say you need more training? Which ones need to have, or saying, hey, you're doing real good, okay? And, what can you do? So we have to think about PGA, practical, graphical, and analytical. So let's look at it from a practical perspective. We have 46 points. Of those 46 points, we have a subgroup size of. We're going to analyze this in a control chart, which we're now calling a process behavior chart because we're driving people's behavior. We're going to take the average of each subgroup, okay, and we're going to look at the range. And we're going to calculate the limits to see if any point is outside of the limits, which says, hey, something's going on that we can say is unusual and we need to react to it. Okay, so we're going to look at the variation within each group, and we're going to look at the variation between the groups. Now, why is this important? Variation within a group says how consistent a person is. If there's very little variation within a group, that says a person is very consistent from day 1, day 2, to day 3, to day 4. More consistent they are, the smaller the variation is going to be. Variation between groups is basically the difference between people. Some people you're going to find are more consistent, and some aren't. And so we're going to see that. So we want to basically understand what that is. Practical perspective, I want to look at the data. So the first thing I'm going to look for is, are there any missing data points? No, there aren't. Okay. Now, The second part, though, is do I have any data points that look kind of funky? Okay, and funky here says different than everybody else. And there are in here 281s and 180. And the question is that what could cause these numbers? What causes these numbers to change? Is it the day of the week? Is it the time of day? Does it have to do with fatigue? What shift were the people on? What was going on there? So we have to look at all that. So I identified that. But here's the data. Here's showing a couple of the data points. I blew it up so at least you can see. So we have the 81 looking at, and we have the 80 down there. There's another 81 down farther. So if you look at it, I mean, those are the only ones that kind of jump out at you. Okay. Graphical. Here's our data. Now we look at this chart. What do we see? Well, we have some things here that are very consistent, but we also have, it looks like, kind of jumping up and down, some cyclical patterns going on here. Okay. We don't see anything except for one data point outside of the limits. We see an awful lot inside of the limits, and the variation seems to change even within the limits if you look at it. So, we have some different things to focus on. So, if I was going to come back and say, is this a predictable group? Well, except for that one data point that's low, it's pretty darn predictable. Okay, with an average of 72. So, this is kind of telling us that, it's pretty good and people are pretty consistent. Okay. Analytically, there I am looking at the 4 days, just looking at histogram. And, as you can see, we have some different shapes, but the thing you probably will notice right away looking at this is that, hey, wait a minute, my scale's changing for each day. So it's kind of misleading looking at this. So what I would do now is I would go in and I would make the scale all the same. So watch what happens when I make the scale all the same. Now we have the same set of data using the same scale for each one. And do we see much of a difference in the pattern? And, if I look at it, it's centered pretty much about the same for each one. Okay. A little bit more variation on the last day. It looks like we got a couple outliers there on the third day. But the first 2 days, man, they're pretty consistent. Okay. So I think, and that's good. But this is one of the things that if you look at data, you want to be able to make sure you're looking at the same set, looking at the same scale. Okay, when I was a young stat magician, I had some engineers trying to take advantage of me, and they tried to say that I have a process that was in control or out of control. And all they did was they took the same set of data and they changed the scale. And by changing the scale, all of a sudden, it got really consistent because why? Scale was so big, everything flattened out, so it looked like almost a straight line. And really, if you put it on a scale that they were actually measuring it to, it was the same thing. So this is the thing that you got to look at, is always look at the scale and see when you're comparing things. Is it the same or is it different? Try to make it the same, because otherwise you're going to get into trouble. From an analytical perspective also, just looking at it on an XY plot, do I see anything different going on? Well, not really. It looks like it's fairly consistent all the way through here. So it's still not varying very much from day one. Day two looks kind of funky though, doesn't it? Day three, things look to settle down, except for, I got one data point way up there. All right. And then day four, hey, I might be able to say there's an increasing trend there, but realistically, it's just random data scattered all over the place. So it's really not telling me much. Okay, so let's talk about the results. There's an out of control data point. Okay, we had one person that had performance much lower than the rest. What should we do with that person? Is that person basically an outlier? And is that outlier good or is it bad? Anybody else do any worse or better than the rest? Are there any significant changes other than that one out of control point? Okay. So what pay should we give the lowest performing person relative to the rest? Should they get the worst? Should we put them on training, retrain them? Okay. And does our chart kind of coincide with any other predictions that we've got that might be? Okay. So if we went and we said we're going to make some changes to the process, and we've got to look at everybody, do we single out the one person that's very low, or do we look at any other to take action for it? And again, is this something that we should do, or would we create more issues by doing it? Well, we talk about it. Who are these people and what is the test? It's the result of the 1997 PGA Masters Tournament. Most out of control person is Tiger Woods. Is he better than the rest? Well, in this case, he was. He's the only one that showed to be of any significant assignable cause. He was more consistent than anybody else there. As a result, he earned $486,000. So, does that mean we shouldn't let him play anymore? Well, some of the other golfers might might want to say, yeah, get him off. We don't want him around because he's taking all our money. But think about it. You have to think about what the impact is and where you're going with it. Okay. So, talked about data. We talked about trends. We talked about what we have to do. The challenge we have is when we start looking at data, how are we going to plot it first? Once we understand how that data is going to be plotted and what kind of data we have, then we can start collecting it in a way that makes sense. And collecting that data is so important. I will say there's more issues that I have seen with funky data because if you tell people to collect it and you aren't precise on how you want it done, surprised with the results you get. And so we want to make sure that you're constantly getting exactly what you want. I've been even so bold enough to tell people in IT that are pulling data for me from databases that this is how I want it to look. Partially because I know what it needs to be, how it needs to be done in terms of doing the type of analysis I might think I'm going to be doing with it, whether it's in ANOVA, whether it is with doing some type of long graph. So, you got to think about that. Okay. So with that, I'm going to open it up if there's any questions. Stephen, has anybody said anything yet? Or
there aren't any questions listed, but maybe we'll give people just a minute to see if they come up with any questions.
okay, that's fine.
Do you want to talk a little bit about what's going to be in the next session while we wait for questions?
Sure. Okay. Next session that we have is going to be one that we're going to start with the very first control chart that was created by Dr. Schuhart back in the 1920s. And that is a variables control chart. We're going to talk about the different types, the different ways that they can be used, and how to basically set them up and make them work. And the challenge here is variables charts can take a variety of forms. And I'm basically going to show how I could take a average control chart, X bar and R and X bar and S, and break it down to even look more closely at it so I can see what is happening day by day, minute by minute, to try to understand what kind of variation is going on. So we're going to be looking at a bunch of different charts. Now, I don't know what kind of software you're using. Sometimes schools use SPSS, sometimes they're using Minitab, sometimes they're using Jump or something else. Okay. It doesn't matter. The thing is that learn your software, learn how to use it, and get comfortable with using it and all the capabilities of it. I showed you two different softwares today. I showed you Minitab in the beginning with the histogram that I gave you. And then I did the analyze part for the case study. I was using Jump, and Jump allows me to put those charts, the histograms, sideways, which is a little different than what most people look at, but it's great for comparing things. And so that's why I wanted to at least show you there's some different ways to look at data and to make sure it works fine.
That sounds great. Looks like some great upcoming information on the next one. We don't have any questions. So just a couple notes. You'll get an email from me, Jenny, and that will have a link to our YouTube channel where you can find this recording and watch it again. And I believe we'll be sending out the slides for you to view as well. Hope you attend the next sessions and look forward to seeing you then. Thanks, Jim, so much.
Great, Jenny. Great. Thank you so much. It was a lot of fun.
See you next time.
All right. Take care.